Okay, so while you're enjoying your sandwiches, I can introduce Frederik Nathan. He is a Dane, so he did his master's and PhD and also bachelor, I think. Maybe not, but at least a special and PhD with Markovian at the condensed matter theory department at the University of Copenhagen. And he also did his first postdoc there. Markovian is now in University of Washington, as you can see, but he was at the NBI at that point. After that, Frederik moved to Caltech to do a postdoc with Gilles Raphael. And now he's back in Denmark and here to give a talk about the master equations, which many of you use. And at least I personally have found the derivation of the master equation quite mysterious, but he claims that he has a much more transparent and rigorous derivation.
Yes.
Which is also more powerful, apparently. So
that's a claim, yes. And like just to assure you, I won't give you the derivation here, so relax. But you can find it here. And also, there's some follow-up work here. Okay, yeah, so I will tell you about, it's called the universal Lindblad equation for open quantum systems. So it's a new master equation which we claim can be used for a large class of systems. Oh yeah, yeah, tak. Okay, yes. So back to the talk. Sorry for the interruption. Yeah, so I will present a new master equation which we claim can be used for many classes of systems that you couldn't reach with previous master equations, and it's a very simple equation, and it's derived rigorously. So you can find conditions where it works, and then you can feel safe using it. So I will give you the details now, and I should say, of course, please interrupt me if you have any questions. Yeah. So the beginning. Oh.
Men til højre der er videre.
Okay, I'll just use my keyboard. So just to give you some background, in case you don't, it's not so fresh in your memory. So when we learn about quantum mechanics, we learn that the Schrödinger equation is a method to use. It's a law, the fundamental law of quantum mechanics. Any quantum system evolves according to the Schrödinger equation. So say if you have a spin in a magnetic field, the Schrödinger equation tells you that the spin will precess indefinitely around the magnetic field. That's the Schrödinger equation. But of course, that's not how it is in the real world. In the real world, the spin interacts with the surrounding environment. There can be nuclear spins nearby. There can be photons. It's connected to the electromagnetic field. There can be phonons. There can be electrons. There can be all sorts of things that we don't really understand and that we don't really control. So of course, a spin does not indefinitely precess around the magnetic field. Eventually it decays and points along the magnetic field. So that means that the Schrödinger equation is not right. There's some other law that governs quantum systems in the real world. So the story is quite similar to classical mechanics. So when we learn about classical mechanics in high school, we learn that they are described by Newton's laws. So if we throw a ball in perfect vacuum with zero friction, the ball will follow a parabolic trajectory, and we can very easily compute it using the forces involved. But of course, when you throw a ball in the real world, it will not follow a perfect parabolic trajectory. It will fall a bit short because of the air resistance. So how do we deal with this? In classical mechanics, it's very easy. We just add a term to the equations of motion that describes the friction. And then we can compute this parabolic trajectory. So the question I will try to answer in this talk is whether there's a similar thing we can do in the Schrödinger equation. Is there a similar term we can just add that will deal with the effects of friction, of all the uncontrolled degrees of freedom in the problem that we don't want to keep track of. So what's the correction to the Schrödinger equation? That's like the hand-wavy goal of my talk. So just to say, the Schrödinger equation, of course, is a very useful equation, but there in almost all fields of quantum physics, it's necessary to understand the effects of the environment. So in atomic physics, the Schrödinger equation, like Bohr model, tells you the distribution of levels, but in order to compute the lifetime of these levels, in order to understand why the electron is always in the bottom shell, we need to take into account the interaction with the electromagnetic environment. And that's the environment, that's the noise that we don't understand. It's the same in nuclear and particle physics. There's some other fields than the electromagnetic fields, but it's basically the same story. The atoms the nuclei can decay. In condensed matter physics, it's very relevant because there we really have a lot of degrees of freedom that we don't understand and that we don't control. So the environment is really, really important. Chemistry, it's the same, like in biology and big molecules. There's also lots of degrees of freedom, lots of noise. And in the present day, we try to build quantum computers. So what all these like fancy wires and plates, really why they're there is because they want to shield off the environment. They want to shield off the noise. But it's of course not possible because otherwise we would have a working quantum computer. So the main obstacle towards realizing a quantum computer is to eliminate the effects of noise, to eliminate the effects of the surrounding environment that disturbs the quantum state. So this is to say that it's very important to understand the effects of environment. So now I will come to the main part of my talk. First, I will review the theory of open quantum systems and some of the common methods that exist. Then I will present our method, the universal Lindblad equation. And finally, I will give a demonstration on a Heisenberg spin chain. So first, open quantum systems. So it's very easy to model an open quantum system. We have a degree of freedom that we care about, say a spin. And then we have an environment. And then this spin is coupled to the environment. The environment can be the whole universe through some system-environment coupling. So this is a very generic Hamiltonian. You could say this is the Hamiltonian for the whole universe, but we only care about the system, the single spin. So how would you solve this? You would, just to make our life easy, let's suppose that the system-environment coupling is just one operator in the system coupled to one operator in the bath, in the environment, through some dimensionless, coupling strength, which we call gamma. So the method that I present works for arbitrary system bath coupling. This is just to make the discussion simple. So how would we solve this problem? Then we could try to solve the Schrödinger equation. So we set up a wave function for the whole universe, and then we evolve it in time. But this is not feasible. Like say the whole universe is 10 to the 26 degrees of freedom, then we need 2 to the 10 to the 26 numbers to just keep track of the wave function. That's impossible. Like that's a very large number. So that's impossible to solve the Schrödinger equation for an open quantum system. Luckily, what we care about is just the system. Any expectation value of the system is determined by the reduced density matrix, which is the density matrix of the whole universe with the bath traced out. And if it's a spin half, which has 2 states, the reduced density matrix is a 2 by 2 matrix. So now we're back from 2 to the 10 to the 26. We are back down to 4 numbers that we have to keep track of. That's a lot easier. So it's not as crazy to solve this problem as it sounds at first. So what's the equation of motion for this reduced density matrix? If it was completely isolated, if this gamma was 0, we would just have the Schrödinger equation, which when translated to the density matrix is called the von Neumann equation, which is that the density matrix evolves with the commutator of the Hamiltonian of this system. But now we turn on the system-environment coupling, and we get some correction. And the whole goal in the business of open quantum systems is to compute this correction. And that's also the goal here. So it's not as easy as for closed quantum systems. And the reason is that this correction depends on the system's past. So a way to understand this is, suppose we have a spin, a system, coupled to an environment. It could be like a continuum of phonons or the electromagnetic field. So this spin like it's in a magnetic field, it precesses around. And then at some point, it interacts with the bath, it decays, and there's an excitation created in the bath. And this excitation sticks around for a while the spin keeps evolving according to the Hamiltonian. And then at some later point, this excitation may affect the system again. So the past will come back to haunt the spin, and it's re-excited. So this tells us that by just knowing the state of the spin, we can't predict its evolution, because we don't know whether there's an excitation here or not. And that's important to know in order to determine the future evolution. So it's not possible to express this correction as a function of the density matrix itself. Rather, it's a function of the history of the density matrix. So it turns out it can be expressed as this in this form, where this f of t is a functional. It's a linear function of this matrix. So it's a mapping of the matrix to another matrix. This expression is well known. It's called the Nakajima-Swansek equation. So this is like the form of the correction, and it is exact, but it's difficult to find this functional f often. So, and also it's pretty inconvenient to deal with if you want to do numerics, that you have to keep track of the whole history of the density matrix. That's very heavy computation. But luckily, in many cases, we can ignore the past. So why can we ignore the past? Suppose the system is just weakly coupled to the bath. So the system is evolving, then it emits an excitation. So it could be like, say, an excitation in an electromagnetic field. We know that after a while, this photon will escape away and never affect the system again. So it sticks around for a while, but only for a finite time. And we can we can call this finite time tau. So the excitations that are created by the system will escape after some characteristic time tau. I will give a definition that works for our purpose, but this is just to say there's some phenomenological timescale associated with the bath, which tells you how fast the excitations escape. Then there's another important timescale in the problem, which is the interaction rate between the system and the bath, like how often are excitations created. And we can call this rate gamma, big gamma. So this tells you what's the characteristic energy scale or time scale for interactions between system and bath. So now we have two time scales, and that's interesting. We can use a ratio that defines a dimensionless number. When this dimensionless number is much more than 1, excitations will escape much faster than they get a chance to affect the system. So the system emits an excitation, the excitation escapes much faster than it can be reabsorbed by the system. Like when this system bath interaction rate is very small. So in this limit, where this time scale associated with system bath interaction is much faster than the correlation time of the bath, we can ignore this memory effect. All memory is instantly forgotten. And that's called the, in that case, it's like a one-way process. All information that's dumped in the bath is instantly thrown away. And in this case, the evolution of the system is Markovian. Like the time derivative of the density matrix is approximately determined by the density matrix itself. So there is an important and commonly occurring case where the memory effect is not important. And in this case, we can put up an equation of motion for the density matrix, which is linear and does not depend on the past. And this is a Markovian master equation. So how should this master equation look? We have just by knowing that it's a density matrix, we have a wish list of properties that we want. First, the density matrix should stay Hermitian. Secondly, the probabilities should sum to 1. So the trace of the density matrix should stay 1. And also the probabilities should be positive. Like negative probabilities don't make sense. So whatever function we have here, it has to preserve the hermeticity, trace, and positivity of the density matrix. And a while ago, a group of people found out that this is how it looks. The most general master equation, Markovian master equation that has these properties should look like this. And this is called the Lindblad form or GKSL form because it was discovered by these people. And there's it can also be a sum of terms of this form. And there's this operator L, which is a very important operator. It's called the jump operator. So it can be any operator. It doesn't have to be Hermitian or unitary or anything. It can be any operator. So it means that any Markovian master equation for the density matrix can be that has these properties can be decomposed in this form. And there's a very nice feature of this master equation, which is both nice intuitively and numerically. It's very easy to solve. Like, so you, even though you have a density matrix, which for like say a 1,000-dimensional system would be a 1,000 by 1,000 matrix, you don't need to evolve the density matrix. You can just evolve like a pure state of the system. And the procedure is that you start with a state, psi, you evolve it through a time step dt by using this effective non-Hermitian Hamiltonian. And then with probability given by the expectation value of L dagger L, you apply L, like the jump operator, to the state. So if you use this procedure, and then you normalize. If you use this procedure for a given, like one realization of this procedure, you would have some continuous evolution, and then suddenly you would jump to another state when you roll the right number with your dice, with your random number generator, and then you would keep evolving continuously. So this is like some kind of mathematical formulation of this picture of quantum jumps that we learn about in quantum mechanics. So there's nothing mysterious about quantum jumps. It's something that emerges from just by having a master equation for the density matrix. And this is, of course, also very easy to do on a computer. So instead of, you can use this as a Monte Carlo approach to solve the dynamics on a computer. And just to give you an example, so suppose we have a two-level system, and the Hamiltonian is just a sigma c matrix, and like we choose the jump operator to be the lowering operator in this two-level system. So suppose you start in the excited state. This could be like a radioactive nuclei or an atom in an excited state. Then you evolve for some time, nothing happens, because the effective Hamiltonian, which is h plus I L dagger L, this is an eigenstate of that Hamiltonian, so nothing happens. But at some point, you discontinuously jump to the ground state, and then you stay there forever. So for given realization, the trajectory would be discontinuous, but if you average over all trajectories, you can very easily see that this should follow an exponential decay law. So this is like, you can say, a formulation of this, say, very simple picture of radioactivity you maybe learn about in high school. It's formulated, can be formulated in terms of these jump operators. So there are several advantages of the Lindblad form. So it preserves the physicality of the density matrix. It's numerically stable. This procedure that I gave before is guaranteed to convert to something, and it's very efficient to use. And it also gives you some intuition, like knowing the jump operator, you know, like what are the incoherent process of the problem. And having intuition about a problem is very important in physics. So this was just based on some very general mathematical considerations. So is it possible to derive this Lindblad form from a microscopic model, like say starting from this Hamiltonian of the universe that I gave before? Can we get to this Lindblad form? So historically, there has been a very common way of doing it, which is so one could think like we take the entire Hamiltonian of the universe, and then let's just perturbatively expand the equation for motion of the density matrix in gamma. And if we do that, we end up with also a very common method called the Bloch-Redfield equation, which is also Markovian, but it's not in the Lindblad form. So the standard perturbation theory in gamma does not give you the Lindblad form. It gives you another method which does not preserve the trace and hermeticity, but not the positivity of the density matrix. So it can both be annoying to solve in a computer because it's expensive, and it can also be unstable. And it also doesn't have this nice intuition that you get with the jump operator. So there's a case, if you take the limit where the energy levels of your system are much larger than the characteristic decay time, in that case you can get a Lindblad form using the Bloch-Redfield equation. And this is basically Fermi's golden rule. It's generalized to this thing called the quantum optical master equation. So suppose you have an atom with electron volts separating the levels, and the lifetime are many, many orders of magnitude slower than this. In that case, it's possible to get a Lindblad form just by expanding the equation of motion of the density matrix to linear order, to lowest order, and then taking this limit that the relaxation rate is very, very slow. And in nuclear physics, it's even better. It's a mega electron volts compared to, say, 10,000 years. That's a very good separation of timescales. So this Lindblad form is very good. This quantum optical master equation is a very good approximation for these problems. And what you end up with is a jump operator for each pair of levels. So there's an incoherent process for each pair of levels, and you can understand it that each transition talks with its own path, it talks with its own wavelength, and they're very well resolved. So in that's just the intuition behind, and that gives you a very good description and a very accurate model for these class of open quantum systems. So we require that the decay rate is much larger than the level spacing. And this is called the rotating wave approximation. So this is what we have in atomic physics. If you imagine putting up the energy levels, and then because these energies have a finite lifetime, they're smeared due to the Heisenberg uncertainty principle. And as long as this smearing is much less than the separation, this is a good approximation, and you have a Lindblad form master equation for this problem. But in cases with many, many degrees of freedom, say a quantum computer, which is an array of qubits, so exponentially many levels, these levels can become very, very closely spaced, and they may also have a very bad lifetime. And in that case, these smeared levels start to overlap, and there it's not possible to use this approximation, and these standard methods break down for these classes of problems. So this brings me to the universal Lindblad equation, which is a Lindblad form master equation, which works both for this quantum optics regime, like atomic physics regime, and for the solid state regime or the many-body regime. So the details of the master equation and the derivation are given here, but I will just summarize it. So the intuition we have, the observation, the first key idea is that we only expect this Lindblad form to arise in the Markovian regime. And I argued before that there's a dimensionless parameter associated with this Markovianity, which is this rate between the system-bath interaction rate and the escape rate of excitations. So we have this big gamma and this tau. So the first step in our derivation is to define these timescales. Of course, there are many equivalent definitions, but for our purpose, we found a definition that works for us. And the definition is we take the Hamiltonian of the universe. So this bath operator, B, has a correlation function associated with it. And this correlation function decays at some characteristic rate. And that's a correlation time, but we define it slightly different. So we take the Fourier transform of the correlation function, which is we call the spectral function. And then we define this weird object that we call the jump correlator, which is the Fourier transform of the square root of the spectral function. So it has the Fourier transform of G has the same smoothness as the Fourier transform of J because it's just related by square root. So that means when you go to time domain, they have the same decay length, roughly. And we take the mean time associated with this. We take and define our big gamma, our system bath interaction rate from this number, and the correlation time from the characteristic decay time of this jump correlator. So these are some definitions, and like check the paper if you want to look through the derivation. So these are just some definitions of these two timescales that we found out worked for our purpose. So that was the first step. We have defined, we have given definitions of gamma and tau. Yes?
Yeah, so you say you define it because it works for your derivations. I'm not so familiar with this, so are we to understand that it's also like a good general?
Yeah.
It doesn't match with whatever.
I mean, you can say, yeah, it's a phenomenological scale, tau.
Yeah.
So you can say there are probably many definitions you can give which capture the same characteristic decay time. This is just one of them. Another one which is common is to just take the mean time associated with the decay of J.
Yeah.
That's another one. And we're able to relate these two timescales. So we found that this tau here is an upper bound for the characteristic decay time of J.
Okay, so different definitions would give you different numbers, but they would be similar.
They would be of the same order of magnitude, yes.
What about the gamma?
The gamma?
This will be more weird.
Yeah, that's a weird, it's a little more weird, so we're also hoping that maybe it's possible to improve this. But gamma is also an upper bound on, there's another characteristic decay time you can define from the integral of the absolute function of the spectral function, of the correlation function, and this gamma is also an upper bound on that. So it's basically, we were able to establish some bounds. So we found out that gamma half is an upper bound for the magnitude of this correction to the von Neumann equation. So there was this delta rho dot that I showed before. The norm of that is bounded by gamma half.
I'm just thinking, I mean, is it obvious that gamma gives you some system bath interaction?
It's not obvious
It
here.
scales with, with gamma, small gamma, whatever it is, but why is it?
It's not
That's
obvious.
equal over G squared.
Yeah, it's not obvious here. It's because this G is roughly, it's a, you can say it's a square root of the correlation function, in the sense that G convoluted with itself gives you the correlation function.
Mm-hmm.
So, and this is like, we were able to rigorously establish a rigorous proof using this. So it's possible that there exists a better bound, which looks less weird. But at least this bound works, and it's also related to it's also gives you a measure of the system bath interaction. Mm-hmm. And it's also probably a very loose bound that we get. But it's just to say that you can define these two timescales. So it's not something that you grab out of thin air. It's something that you can sit down and compute. Okay, so these are the two timescales that we use. So step 2 in our approach is, as I said before, just expanding linear order in gamma doesn't give you a Lindblad form mass equation. So we have to do something different. And the different thing we do is to perform a mapping of the density matrix. So we map the density matrix to this rho prime, which is rho plus some small correction. This m is some linear function of rho, which is well defined, which an expression is given in the paper. So this operator has an important property that the time derivative of this term gives you the difference between the Bloch-Redfield dissipator and a Lindblad form dissipator, which I give you shortly. So, and secondly, the magnitude of this correction is bounded by this gamma tau, like this dimensionless Markovianity parameter. So whenever gamma tau is small, whenever the dynamics are Markovian, the density, the rho prime and rho are the same. So in our imagination, like rho and rho prime are basically the same. Whether you use one or the other, it gives you the same result. But even though they're the same, their time derivatives don't need to be the same. So and that's the idea, that you can map the system to a different frame where the density matrix is almost unchanged, but its time derivative may be different. So this is this is our idea. And by defining M properly in a way that obeys this expression, we're able to find an equation of motion of rho prime, which is in the Lindblad form. So, of course, it's an approximate result, so there's some correction. But I will give you the jump operator first. Oh, yeah, this is a correction. This is the jump operator that we get. So you can see that X is the operator that we couple to the system. We put in, sandwich in these projectors into the eigenstates of the Hamiltonian, and then we weigh it by the square root of the spectral function. So you can see this as kind of the square root of Fermi's golden rule. If you take the transition rate between two eigenstates in this master equation, you'll recover Fermi's golden rule. But this also gives you the off-diagonal elements of the density matrix. And then we have the correction, which is bounded by this number 2 gamma squared tau, while we're able to establish that this term here is bounded by gamma half. So you can see that the correction is subleading in this Markovianity parameter. So in the limit where gamma tau is small, we expect that the correction is insignificant, and we also expect that rho and rho prime, and we also know that rho and rho prime coincide. So that means that in the limit of small gamma tau, this is an accurate master equation for the system. And we didn't assume anything about the level spacing of the system. So we can apply this to a 2-level system. We can apply this to a 1,000-level system. And it doesn't matter how closely spaced the levels are. The only thing that controls the validity is the properties of the bath and the system bath coupling, the Markovianity of the bath. So the relative error is given by this dimensionless number. And we're able to quantify, so suppose you solve this master equation. We know that if we have an open quantum system, the true density matrix will saturate at some steady state. That's a very, so there is an exact expectation value of your operator. And then you can try to solve the same problem using this master equation, which you call the ULE. And now you can ask yourself, what's the deviation in the expectation value between the exact result and the one used using the master equation? And we're able to bound this. And it's bounded by some constant, which is some constant that we can compute, times gamma tau. And this constant c is some finite number. So we're able to rigorously establish that the steady state of the ULE and the exact expectation value, they coincide in the Markovian limit. And the details of the derivation are given in this paper here. Yeah, so, and there's a procedure for computing this operator, this number c, also given here. So there are some very nice features of the ULE compared to existing methods. That I didn't explain. So we can use it for multiple baths. So for each bath, there is a single jump operator. So if you have one bath, no matter how complicated your system is, there just is one jump operator. So that compared to the quantum optical master equation where you have a jump operator for each pair of levels, this is a big simplification. You can use it for arbitrarily time-dependent Hamiltonians. That's given in this, the definition is, the procedure is given in the PRB. And you can show that in the limit where the time dependence is lower than the correlation time of the bath, you can basically ignore the time dependencies of the Hamiltonian, and the jump operators just relax in the instantaneous basis of the Hamiltonian. And it reproduces Fermi's golden rule in the limit where we expect Fermi's golden rule to be valid, namely when the decay rate is smaller than the level spacing. And the jump operators are quasi-local. So I will get back to this soon. Yeah, so this is basically, now I'll show this quasi-locality. So just to give a demonstration, we can take a Heisenberg spin chain of 12 sides. So it has a Hilbert space dimension of 1024. So that would be very hard to solve using existing methods, and the quantum optical master equation would not be possible to use because it has so many levels. We take and connect the outermost side to a bath, and then just as a start, like let's try to compute the jump operators. So this class of problems has been studied before, and in these cases what you had, the method you had up to this point was a phenomenological approach where you would say this bath wants to relax the outermost spin, so why not approximate the jump operator with the lowering operator on this spin. But now now it's possible to get the jump operator systematically and with a rigorous bound on the master equation. So what we get if we do this using some parameters, I have written them down here. Yeah, so the way we get the jump operator is that it's given by this expression. We can write it out differently as a convolution of the Heisenberg evolved sigma x1 with the jump correlator. And as I said, the jump correlator is the square root of the Fourier transform of the jump operator. The jump correlator is the square root of the spectral function. So the Fourier transform of the jump correlator has the same smoothness as the Fourier transform of the spectral function, which means that the jump correlator has the same decay properties as the like canonical correlation function of the bath. So it decays on this characteristic timescale tau. So now we can try to get the jump operator. So at time 0, the Heisenberg evolved sigma x1 just has support on the outermost side. And then as we evolve, the supports spread into the bulk of the chain. But there's a cutoff. When we reach tau, like we know that the jump correlator has decayed. So we only get the contributions from sigma x1 at small times, which means that the jump operator will just have support on the first few sites. So this tells us if we have a bath, the associated jump operator only has support near the bath, which is nice. This is like what we would expect from physical intuition. And now I will give you a numerical example with this Heisenberg spin chain using the parameters I showed before. The phenomenological approach would just give you a jump operator with support on the leftmost side. But now we do the actual computation using some actual parameters with this ULE approach. And what we get first is we get a large contribution from the first side. And if you look, this looks a lot like the lowering operator, but there's also a component which contains the raising operator. But there are also some corrections to this jump operator. And these corrections have support on the further side in the chain. So it's possible to say that actually this phenomenological approach wasn't so stupid. It was actually pretty accurate, but now it's possible to get the corrections systematically. And we can solve the master equation and verify that the magnetization of the spin chain relaxes to the value we expect from a thermal equilibrium state at the temperature of this bath. That's the gray line I write here. We can also get some non-trivial features. Suppose we connect the other end of the chain to a hot bath. Then this saturates into a non-trivial steady state, which cannot be described through an equilibrium distribution, and we're able to get this non-equilibrium steady state of the spin chain, get the magnetization. And then, there also runs a current here. So we have a hot bath and a cold bath. We know that energy will run from the hot reservoir to the cold reservoir through the chain, and also magnetization, because Magnon number is conserved in this Heisenberg spin chain. So, and why do I mention this as a particular example? It's actually because of a paper written by Ashak. We know that the steady state value of the current and the exact steady state value of the current and the ULE steady state deviate by a number controlled by this gamma tau. But also, the current itself is controlled by the system bath coupling. So the magnitude of the current scales with the system path coupling too. So this, you could say, this is an example where the Lindblad approach breaks down. Like it cannot be used to accurately compute the current through the chain because both the correction and the current itself scales linearly with gamma. So this was pointed out in this paper by Archak and collaborators. So we read this paper very closely and thought about it. And we found out that there's a solution to this problem. So there are two cases where you don't have to worry about this. There's namely the correction actually of the current, of the non-equilibrium current, actually scales as gamma squared tau, which means that the relative correction still goes to 0 in the limit of Markovian dynamics in two important cases. If the length of the system is so large that the jump operators don't have support in the bulk of the chain, the correction to the current scales at the squared system path coupling and the relative correction goes away. But even if you don't have a large system, you can still compute the current accurately by taking into account this transformation M that's given in the paper. So it's slightly more involved, but it's a well-defined procedure and you can still exploit the stability and the intuition of the Lindblad master equation. The details are given in this paper. So that was an important subtlety that we encountered, but there is a solution to this subtlety. That's the message. So now I'm at the end. So we have a Lindblad form master equation, which we can use to describe any quantum system coupled to a Markovian path. It's a rigorously derived master equation with some error bounds controlled by this gamma and tau. And the relative derivation of observables is controlled by this dimensionless number, including relative correction of currents, either if you have a large system or if you take into account this correction of the frame. And you can apply it to many-body systems, driven quantum systems, any quantum system, no matter what the level spacing is, no matter even if it has a chaotic time dependence, you can use this master equation. And as an indication that this is maybe not a stupid idea, a lot of people got the same idea at the same time independently. So the first one was this from 2018. Gediminas was actually also a postdoc at NBI, the rest are in Lund. So we used it for a project in 2019, but there's a lot of other people that got the same idea at the same time. So what our work from 2020 does is to all these works like phenomenologically, like got to this master equation on phenomenological arguments. They said, this is the square root of Fermi's golden rule. Maybe this is a good way of doing it. When you plug in the simulations, it works pretty well. And there are some more or less rigorous derivations, but none of the derivations were fully rigorous. So this was what we did in 2020, was to put this master equation on rigorous footing and find this important physics that we have these two energy scales, timescales, that controls the validity of the master equation. And finally, we found a way to generalize it to arbitrary system path coupling and arbitrary time dependence. And so now, what to do now is to apply this to problems where you have open quantum systems, but like existing methods don't really work so well. So it's already been done by many groups, like our collaborators in Copenhagen that are using this method to devise protocols for extracting informations of Majorana qubits. There's a group that has studied xenolocalization in many-body systems using this method and readout schemes in nuclear spins. And matrix product states, this method is very, it's a very natural thing to use this method in matrix product state formulations. So that's already also been done. And one thing that we're thinking about is to use this method to characterize multi-qubit errors in quantum computers, where this is also a very natural method to use. So, but there may be other applications of the method. So other things that we're thinking about is to include higher order corrections in this gamma tau. And like, yeah, to investigate this method and to investigate the steady state of the master equation. And yeah, a final thing is to see if we can get better error bounds, because as you said, it looks a little bit weird with this gamma, how it's defined. Maybe there's a better error bound out there that we can get. So the error bounds that I present, they are upper bounds, and as with most mathematical upper bounds, they're often pretty loose. So we expect that in reality, the error is much smaller, and we are trying to see if we can get a better rigorous error bound. So yeah, that's the end. So thank you for your attention.